For 50 years, we thought we understood Sagittarius A, the supermassive black hole at our galaxy's center. We called it dormant, predictable, a 4 million solar mass giant that barely flickered compared to the violent quasars in distant galaxies. But in 2023 and 2024, the James Webb Space Telescope revealed something that has astronomers scrambling to rewrite their models. Sagittarius A is flaring constantly, erupting with bright bursts 5 to 6 times per day, with no periods of rest. The activity appears completely random, defying every pattern scientists expected to find. Sagittarius A contains the mass of over 4 million suns, all compressed into a sphere so dense that its event horizon, the point of no return, spans about 25.4 million kilometers across. To put that in perspective, Earth sits 150 million kilometers from our Sun, while Mercury orbits as close as 46 million kilometers. This means the entire point of no return around our galaxy's central black hole would fit comfortably inside Mercury's orbit. For decades, astronomers watched this cosmic giant with a mixture of fascination and frustration. Sagittarius A appeared relatively inactive compared to other supermassive black holes, earning it a reputation as a sleeping giant. Unlike its more distant galactic cousins, including quasars, the Milky Way's black hole didn't seem to be consuming much material, and as a result, it was remarkably dim in X-ray light by comparison. When scientists used the Chandra X-ray Observatory to observe it intensively, they discovered something puzzling. Sagittarius A actually consumes less than about 1% of the material it has available to it. This wasn't the behavior scientists expected from a supermassive black hole. Most black holes of this size should be voraciously feeding, creating brilliant accretion disks as matter spirals inward at incredible speeds. But Sagittarius A seemed almost polite. It would occasionally flicker with activity, infrequent flares that barely registered compared to the violent outbursts seen in distant galaxies. These sporadic events followed predictable patterns, with long quiet periods punctuated by brief moments of brightness. The black hole's environment told the same story of restraint. Sagittarius A is surrounded by a dense cluster of stars, some of which orbit so close that they complete their journey around the black hole in just a few years. Scientists tracked these stellar dancers meticulously, using their orbits to confirm not just the black hole's existence, but its precise mass and location. Everything seemed stable, predictable, almost mundane for such an exotic object. This baseline of calm activity became the foundation for our understanding of galactic centers. Sagittarius A was the textbook example of a dormant, supermassive black hole, massive enough to anchor an entire galaxy, yet gentle enough to allow complex stellar neighborhoods to flourish in its immediate vicinity. From its position 26,000 light-years away, only 1 in 10 billion photons of visible light could reach Earth, most absorbed by the gas and dust that clog the galactic center, making it a challenge to observe but seemingly straightforward to understand. For nearly 3 decades, this understanding held. Observations from the Chandra X-ray Observatory, infrared telescopes and radio arrays all painted the same picture: a quiescent giant, occasionally stirring but fundamentally stable. The pattern was so consistent that it became the baseline against which all other black hole behavior was measured. 3 decades of patient observation ended abruptly when the James Webb Space Telescope turned its infrared eye toward Sagittarius A throughout 2023 and 2024, with results published in 2025. What astronomers discovered shattered their understanding of our galaxy's central black hole. Instead of the predictable, sporadic flares they expected to document, Webb revealed something unprecedented. Sagittarius A was flaring constantly, erupting with 5 to 6 major flares per day, along with continuous smaller flickering events, creating a non-stop sequence of activity. Floating 26,000 light-years from Earth and watching this cosmic giant through Webb's infrared vision, the scene would be unmistakable. A constantly changing, bubbling glow, and then, suddenly, boom! A massive flare appeared out of nowhere. Then everything would calm down again, only to repeat the cycle minutes or hours later. Each observation revealed different and surprising activity, with no defined pattern that scientists could predict or explain. The scale of this activity defies everything astronomers thought they knew about black hole behavior. During these flares, the brightness can increase by more than 10 times the baseline level, creating bursts so intense they would be visible across vast distances if they weren't shrouded by galactic dust. Multiple flares come one after another, like a firework happening before it goes quiet. This happens a few times a day, creating a light show that never truly stops. Webb's near-infrared camera captured this unprecedented activity during 48 hours of observations spread across multiple sessions over 1 year between 2023 and 2024. The telescope's extraordinary sensitivity allowed astronomers to detect not just the brilliant major flares, but also faint flickers and smaller flares occurring between the major events. What emerged was a picture of relentless activity, a black hole that never rests, never returns to the quiet baseline that defined it for decades. The implications of this discovery ripple through our understanding of galactic physics. Flares are a common feature of supermassive black holes, but Sagittarius A stands out due to its constant variability. Throughout 2023 and 2024, observations showed something new every time, with no stable state ever reached. This represents a fundamental shift from the dormant giant astronomers had studied for decades to something far more dynamic and unpredictable. The randomness of the activity particularly puzzles scientists. Unlike the predictable orbital mechanics of the stars around Sagittarius A, or the regular pulsing of distant pulsars, these flares follow no discernible pattern. The activity occurs over varying timescales, ranging from brief, faint flashes lasting mere seconds to longer, more intense eruptions. Some flares build gradually, others explode without warning, and the intervals between major events vary wildly from hours to minutes. This chaotic behavior suggests that something fundamental has changed in the environment around Sagittarius A, or that our previous observations simply lacked the sensitivity to detect what was always happening. The James Webb Space Telescope's unprecedented infrared capabilities have essentially given astronomers, given that Webb detected 5 to 6 major flares per day with 0 periods of rest, do you think this constant activity was always happening and we just couldn't see it? Or has Sagittarius A fundamentally changed its behavior? Comment your answer below. Either way, the implications for what's causing this relentless activity are about to get even stranger. In April 2024, using the MIRI instrument on board the James Webb Space Telescope, an international team of scientists made the first ever detection of a mid-IR flare from Sagittarius A. Research indicated a connection between the observed variability at millimeter wavelengths and the observed mid-IR flare emission. This represented a breakthrough moment. Astronomers were now detecting Sagittarius A's flares across multiple wavelengths simultaneously, revealing the full scope of its chaotic behavior. The most puzzling discovery emerged when astronomers began analyzing the timing of these multi-wavelength flares. For the first time, scientists observed that the shorter wavelengths of the flares changed brightness slightly before the longer wavelengths. The shorter wavelengths brightened first, the blues and purples of the electromagnetic spectrum, followed seconds later by the longer wavelengths, the reds and infrareds. This tiny delay, mere seconds in cosmic terms, represented something unprecedented in black hole physics. The sequential brightening suggested that particles were losing energy as they traveled outward from the black hole, creating a cascade effect that revealed the internal dynamics of the flaring process. Simultaneous observations with the sub-millimeter array, SMA, the Nuclear Spectroscopic Telescope Array, NuSTAR, and the Chandra X-ray Observatory filled in additional parts of the story. The SMA detected a millimeter wave flare lagging roughly 10 minutes behind the mid-IR flare. This extended the time delay pattern even further. What began as seconds between infrared wavelengths stretched to minutes between infrared and radio emissions. These time delays weren't random glitches in the data. They represented a fundamental signature of how energy propagates through the extreme environment around Sagittarius A. The pattern suggested that each flare begins near the black hole's event horizon and then expands outward, with different wavelengths becoming visible as the energized material travels through the surrounding space. It was like watching ripples spread across a cosmic pond, except these ripples were made of high-energy particles moving at significant fractions of light speed. Even more disturbing was evidence that Sagittarius A had flared dramatically sometime within the past few hundred to 1,000 years, according to X-ray emissions observed by the James Space Telescope. The cloud surrounding the black hole appeared to be glowing in response to a past outburst from Sagittarius A. The X-ray telescope had detected light echoes, a ghostly record of ancient violence that only now was becoming visible to our instruments. This meant the black hole's chaotic behavior wasn't new. It was simply that we had finally developed the sensitivity to witness it. Magnetic reconnection events emerged as the first leading hypothesis. In this model, magnetic field lines threading through the material around Sagittarius EO would occasionally snap and reconnect violently, like cosmic rubber bands breaking and reforming. These events would form transiently orbiting flux tubes, large bubbles of electrons heated by reconnection and threaded with a predominantly vertical magnetic field. The energy released would be equivalent to billions of nuclear bombs in a fraction of a second. The theory seemed promising. It could explain both the random timing and the intense brightness of the flares. But the magnetic reconnection model struggled with sheer frequency. While reconnection events do occur around black holes, the constant daily flaring that Webb detected would require an almost impossibly active magnetic environment. The mathematics suggested that Sagittarius A would need to be processing magnetic field energy at rates far exceeding what theoretical models predicted for a black hole of its size and feeding rate, a fundamental mismatch between observation and theory. The second hypothesis proposed that hotspots were forming in the accretion disk, localized, heated regions where material spirals toward the event horizon. When chunks of material heat to extreme temperatures near the innermost stable circular orbit, they transform into hotspots, where particles become relativistic and emit synchrotron radiation. In this scenario, glowing embers would circle the cosmic drain, each one briefly brightening before being consumed. Yet the hotspot model faced its own crisis. For hotspots to explain the observed flaring pattern, they would need to form and dissipate with a regularity that didn't match the chaotic nature of what Webb was detecting. The orbital mechanics were too predictable to account for random bursts occurring 5 to 6 times daily. The model's internal consistency, its greatest strength, became its fatal weakness when confronted with genuine randomness. The third leading theory suggested that stellar winds from nearby massive stars were feeding material to Sagittarius A in unpredictable bursts. The galactic center is crowded with massive stars whose winds could collide and form gas clumps within the accretion flow, creating an irregular feeding schedule. When the black hole received sudden meals of stellar material, temporary flares would result. The theory had appeal because the variable fuel source could plausibly explain variable output. Yet even this stellar wind model failed to fully explain the observations. The energy output during the flares exceeded what could reasonably be generated by sporadic feeding from stellar winds alone. Moreover, the multi-wavelength timing delays that Webb detected suggested the flares originated very close to the event horizon, not from material being fed from the more distant stellar winds. Each hypothesis, when tested against the full dataset, collapsed under its own contradictions. None of them could simultaneously explain the frequency, the intensity, the timing delays, and the randomness of what Webb was observing. For the first time in decades, astronomers faced a phenomenon their most sophisticated models could not accommodate. Sagittarius A's erratic behavior forces a reckoning with everything astronomers thought they understood about how supermassive black holes influence their galaxies. Recent discoveries revealed that Sagittarius A had flared dramatically within the past few hundred to 1,000 years, suggesting its current hyperactivity might represent a return to its natural state rather than an anomaly. This realization confronts scientists with an unsettling possibility. The relationship between black holes and galaxy formation might be fundamentally different from what decades of observation suggested. The timing delays Webb detected between different wavelengths weren't technical curiosities. They revealed the internal mechanics of how black holes process energy near their event horizons. When shorter wavelengths brightened before longer ones, with delays stretching from seconds to minutes, it suggested that energy was propagating outward from Sagittarius A in ways current models couldn't predict. This sequential brightening pattern had never been observed with such precision, indicating that the physics operating around our galaxy's central black hole were far more complex than anyone had imagined. The implications ripple outward across the universe. Observations with the James Webb Space Telescope revealed early universe galaxies where central black holes grew far faster than their host galaxies, seen just 800 million years after the Big Bang. This discovery suggested that the relationship between black holes and galaxy formation was more complex than the orderly coevolution scientists had assumed. Perhaps Sagittarius A's chaotic behavior represented a fundamental aspect of how supermassive black holes operate. Not the exception, but the rule. Powerful radiation from active supermassive black holes can slow star formation not just in their host galaxies, but in galaxies millions of light-years away. If Sagittarius A was exhibiting constant activity, it meant that our galaxy's central black hole might be influencing stellar birth and death processes throughout the Milky Way in ways astronomers had never considered. The constant flaring raised questions about the long-term stability of our galactic neighborhood. For decades, astronomers had assumed that the relatively calm environment around Sagittarius A allowed for the complex stellar ecosystems that populate the galactic center. But if the black hole was capable of sustained, violent outbursts, it suggested that the conditions for life and planetary formation throughout the Milky Way might be far more precarious than previously believed. New observations using the IRIS instrument showed that several dusty objects follow stable orbits around Sagittarius A, with the black hole being less destructive than previously thought. This created a paradox. How could Sagittarius A simultaneously be flaring constantly, yet maintaining stable orbital relationships with nearby objects? The answer might lie in understanding that black holes operate on multiple timescales simultaneously, exhibiting violent short-term variability while maintaining long-term gravitational stability. The implications extend beyond our galaxy. Recent discoveries of massive black holes in nearly starless regions suggest that some black holes might be primordial objects dating back to the birth of the universe, fundamentally challenging our understanding of how these cosmic giants form and evolve. If black holes like Sagittarius A could exhibit such unpredictable behavior, it meant that our models for how they influenced cosmic evolution needed complete revision. Humanity had been observing Sagittarius A for 50 years, while missing its most fundamental characteristic. The constant flaring that Webb detected revealed a black hole far stranger and more dynamic than anyone had imagined. Subscribe for the latest cosmic mysteries, and watch this next to see what other black holes are hiding in our universe.